Good afternoon, everyone. My name is Hera Alfa, and my partner is Hery Irdiantoro. Here, we would like to give a presentation about the optimization of solar power system and micro hydro in district Daya-Manokwari. Alpha Mountains Regency is located 33 miles away from Manokwari, the capital city of West Papua, Indonesia. This area is famous with their unique natural resources. District Taige is one of the districts located in Alpha Mountains Regency, lived by 1,290 people. West Papua is endowed with a wealth of hydropower and solar power potentials. The geographic situation of West Papua suggests that there are possibilities of solving some rural electrification problems using PV or microhydro. The solution recommended for power requirements in rural areas that are not very demanding and the sites considered are usually far from existing grids where a single power source cannot technically and economically be envisaged. We can use other sources to form a hybrid system. This is the case for the Tiger District site in the Manokwari, West Papua. Diesel generator is relatively cheap, the technology is widespread, and the power plant construction time is relatively very short. For these reasons, the solution is commonly used for electrification in remote areas where the utility is not usually available. However, the sites are not always accessible and the maintenance of such system is very poor. Because fuel and spare parts have to be obtained from the city combined with the continuous fuel price fluctuations, this solution is not recommended for poor rural dwellers. A hybrid energy system where electricity is generated using multiple renewable sources significantly improves efficiency and the sustainability of such a system. This is therefore recommended for rural areas. Main objective. First, we use RetScreen and Homer to simulate and find the optimum configuration for fulfill electricity demand in District Taike, Manokwari, West Papua. Finding optimum combination, the hybrid power combination to generate electricity by Homer legacy. Finding the optimum financial viability from generating electricity power by RetScreen. Basic configuration. The electric current and voltage of PV power varies with different solar intensity and environmental temperature, and thus the output of PV power is unstable. If the PV array is incapable to real-timely track the change of external environment, the overall efficiency of PV power system will decrease inevitably. The technology of maximum power plant tracking or MPPT is developed to continuously obtain the maximum power output at any sunshine and temperature. Existing MPPT methods mainly include constant voltage method, perturbation and observation method, the incremental conductance method, variable step perturb and observe method, fractional short circuit current method, neural network, the optimal gradient method, etc. With a twin shaft tracking device and MPPT, the power output of PV array is only determined by solar radiation and temperature comparing standard test conditions and general cases. The PV power output can be derived on the basis of the model as shown in equation 1. That, and then calculating PV voltage. The formula is like in the slide. Here we would like to find the reverse saturation current at any other temperature, and then to the case where IPV is 0 or open circuit case, one sees that the reverse saturation current at a reference temperature or TGRF is given by those equations. So we got the current of PV is like in a formula. And then the annual PV power for PV module with 315 watt peak. The data we got from NOA, and we get to we know that the lowest PV power is in June to August, and the highest is in October to November. In the design of Tiger Micro Hydropower Plant, river falling gross is 45 meter and 11 meter head loss, so that the effective height of bore falling is 34 meters, using a water flow rate 0.096 meter cubic per second. Then the amount of power theoretically is. To calculate the amount of power is awakened by using the formula of theoretical power potential multiplied by efficiency of the turbine generator and the network known as the overall efficiency. That is um, 0.6 until 0.7, and in this case we use 0.7. And then why we're using Homer legacy? Uh, we use Homer legacy because we in the configuration we using hydropower and PV, and then we combine it with diesel. And this is the load profile and global radiation in Homer. And we know that the lowest radiation is from July to August, and the highest is October, November, or February to March. So the site has annual average horizontal irradiation of 5.93 kilowatt-hour per meter square per D. This horizontal radiation allows. The load profile corresponds to needs of the village. At night time, the electricity needed mainly for lighting. During daytime, it's used for small industries. Therefore, using Homer, the constraints that best fit the running conditions can be freely chosen, depending on the available facilities, the minimum renewable energy fraction, the minimum PV energy fraction, and so on can be chosen as well. Finally, there is a set of sensitivity variables that can help in choosing the best technical, economical, or environmental solution. Homer accepts either monthly or hourly stream flow data. So an hourly data set has been created for the micro hydro plant by assuming that the stream flow remains constant throughout each day. The resource input describes the availability of solar irradiation and hydro flow rate for each hour of the year. For solar and hydro resources, we have imported data from properly formatted files. And so here's the data we got from the hammer, and we get the COE, or cost of electricity. The best is where the combination is hybrid of PV system and the micro hydro system. So this is the optimum that we got. So the conclusion: this paper was devoted to simulating and sizing micro-hydro PV hybrid system for rural electrification. From the results of the system we have designed, it's recommended to implement similar systems in similar sites. We have compared different combinations of component sizes and quantities and explored how variation in sources availability and system cost affect the cost of installing and operating different system designs. This could be enough to take a decision concerning on electrification of a remote area in a developing country.
Okay, the next is why we use RetScreen. We use RetScreen because we choose it for financial analysis. This is the data from the RetScreen for the Manokwari, and then from here we know that the amount of air temperature, relative humidity, daily soil radiation, atmospheric pressure, wind speed, earth temperature, heating degree days, and cooling degree days based on data from NASA. And the next is, this is the proposed case power system. For the base load, we choose the hydro turbine, and for the analysis type, we choose the method 1. Why we choose method 1? Because it's the simplest one method. And then for the turbine, we want to get the power at least 26 kilowatt, and the price is $30,600. And for manufacturer, we choose Hydro Innovation, and the model of the turbine is COSPRO with capacity factor 80%. And from that, we can get the electricity exported to the grid is 180 megawatt hour. And for intermediate load power system, we choose technology photovoltaic, where in photovoltaic we choose 73 unit photovoltaic, and it will generate electricity at least 23.36 kilowatt, and for the price of 73 units are $36,500. And for the capacity factor 15%, we get the electricity export to the grid are 31 megawatt hours, and the electricity export rate is $100 per megawatt hours. And this is the proposed case system summary. The power total is, for total capacity is 49 kilowatt, and energy delivery is 211 megawatt hours. And this is for emission analysis. For Indonesian, ton CO2 per megawatt hours is 0.709, and for greenhouse gas emission factor in Indonesia is same. And then electricity export to the grid are 211 megawatt hours, and then we choose the ton CO2 is equivalent to cars and light truck is not used, is equal with 24.6. And from the greenhouse gas reduction income, we get that $10 per ton carbon dioxide, and greenhouse gas reduction credit duration for 30 years. And it is financial analysis. The financial parameters, inflation rate is 5.5%, project life 30 years, and debt ratio we choose 40%, and debt interest rate we choose 7.5%, and debt term year is 20 years. And the initial cost overall is, for the power system, is $67,100. And then from the annual cost and debt payment, we get the, for debt payment 20 years is $2,633, and for full cost proposed cash we choose 0 because we don't use full cost. And the annual savings, we get that the total annual saving and income is $22,425, and the financial viability pre-tax IRR equity is 53.1%, pre-tax IRR effect 34.2%, and simple payback is 30.3, and for equity payback in year is 2.1 year. You can see from this graphic, for the before 2.1 year, our financial is negative, but after 2.1 year, we get the income and it grows rapidly. And the next, we goes to the simulation. This is the Homer simulation. In Homer simulation, the first we choose is primary load. This is the primary load for the district arc in the Manokwari. We choose the day-to-day 15% and time step 20%, and scale annual average is 492 kilowatt hour per day. Okay, and then we next setting the hydro. In hydro, the capital cost, as you see here, and the replacement cost, oil, and manufacturing cost, lifetime, we choose 25 years, and the turbine available head is for 40 meter, design flow rate, from that the data is 96 liter per second, and the maximum flow ratio 50%, and for the minimum flow ratio, and the efficiency we choose is 70%, and generator type that we use is RC generator. And for the next, we choose the generator or diesel, where we want to choose 10 kilowatt and 20 kilowatt, as you see from here. Okay, and the next, we setting the PV, and the size of PV we choose 10 and 20 kilowatt. For the lifetime 25 years, the rating factor 80%, slope degrees 1.1, and azimuth degrees west of south 180 degrees. Ground layer reactancy 20%. Okay, and then we choose the converter. This is the setting for the converter. The inverter input lifetime 5 years and efficiency 90%. Okay, after that we go to the solar resource. This is for the solar resource, the data from the Homer, and then we choose to calculate it. Okay, running the simulation, and we get that the combination in this calculation, we get the optimum combination is combination of photovoltaic and micro hydropower, with the cost of electricity is 0.132 dollar per kilowatt hours. This is for the simulation in Homer, and then next to the RetScreen, this is the simulation in RetScreen. As I said before, okay, and this is the data from the RetScreen that we get. Okay, back to the slide. This is the final, our presentation, the end, and thank you.